In your introductory physics class, you likely learned that we can often treat rotational motion in many of the same ways that we treat linear motion. We're going to start building on that conceptual foundation by introducing the concept of angular momentum and then trying to build a sort of analog of Newton's laws for angular momentum, just like we did for linear momentum. All right, so the angular momentum is typically denoted with the symbol uppercase L. The angular momentum of a particle with trajectory r of t is equal to r of t times the cross product with p of t. Okay, notice that because we're using the cross product here, this definition is specific to 3 dimensions. I'll let you think about how we would need to generalize it if we wanted to go to other dimensions. All right, now this object doesn't look exactly like momentum. It seems to include both position and momentum. So we might wonder why it ought to behave anything like ordinary momentum does. In order to see why it might be useful, let's introduce another object called the torque. Now, in the textbook that I'm using in the course, Taylor uses capital gamma for the torque, but I will not do that. I'm going to use what I think is more conventional, lowercase tau. The torque on an object which is experiencing a force is equal to the position of that object cross the force itself. So this is the definition of the torque due to a force F. All right. And we will see that torque plays a relatively analogous role in Newton's Newton's laws for rotation as force does in Newton's laws for linear motion. Okay. Now, let's go ahead right away and state something up front, which is that we can get something like Newton's second law for torque. And the way that we'll do it is as follows. Let's take a derivative of this equation. So we'll have L dot is equal to, well, first we take a derivative of R. So we get R dot cross P. Then we add, because of the product rule, R crossed with P dot. You might wonder if the cross product works in the same way through, if the product rule works in the same way through cross products, and in fact it does. Nothing very funky going on here. Now, in the first case, let's take P and re-express it as M times R dot. Recall that the cross product of 2 vectors which are parallel is 0, and since R dot appears in both factors here, this first term is actually 0. In the second case, remember that P dot is equal to the force on the object. So this is actually just equal to F. So what we get here is R cross F. But by this line here, that's exactly the torque on an object. So while we'll get there in a moment, we have something analogous to Newton's second law for angular momentum, but it's different in a really important way. Notice that an object can have force on it, and therefore can have its motion affected by impressed forces, while not having any torque on it at all. The way that that could happen is if we have a force which is collinear with R. So let's draw a little picture. Suppose that we have an object here. Here's our origin. So this is the vector R. Suppose we have a force on that object that points in this direction. This force absolutely affects the motion of the object, but it doesn't cause a torque. So when we state Newton's first law, or the analog of Newton's first law, we can't actually proceed in the way that we would want to. We would want to say something like, an object continues on some known trajectory unless it is driven to change that trajectory by impressed torques. But we can't do that. The only thing that we can say if the torque is equal to 0 is that L dot is going to be equal to 0. In other words, L is going to be a constant. Constant vector. Okay, But that doesn't feel in the spirit of the first law, which is supposed to allow us to determine the trajectory of objects. So we'll say that for the first law, we just need to use Newton's first law, the ordinary one. All right. Now, the second law, we've basically just shown it. And let's just, put it over here so that we can put them in a nice order. So it's going to be that L dot is equal to tau. Wonderful. Okay, so now to some degree we've said everything there is to say about the first two laws for rotation. So let me make sure that that's clear for rotation. We've also derived this principle here, which we could call conservation of angular momentum. If an object experiences no torque, then its angular momentum is constant. However, we also made the argument that these two laws do not allow us to solve for the trajectory of an object given known torques. But there is a setting in which we can say a little bit more, and I want to explore that now. So let's look at the second law for torques in the setting where we're constrained to move on the plane. In that case, the only torques which will have any effect are torques which point in the z direction if the plane is the xy plane. All right, so let's do it. We'll have that r of t. Now, I want to work in polar coordinates. So look back at lecture 2 where we talked about polar coordinates and polar unit vectors. So r of t is r of t times the r hat vector at t. And actually, I guess just for conserving board space, let's write these all without arguments. So we get r is equal to r hat. And r dot is equal to, well, we worked that out too. It's going to be r dot r hat plus r phi dot phi hat. Great. Now let's work out what L is. So L is equal to r hat cross r dot r hat plus r phi dot phi hat. Okay, now since the r hat vector appears here and here, this first term doesn't contribute at all. Okay, so I can just cross that out. For the second term, we need to think about what direction the r hat cross phi hat vector points. Let's do that up here. So here I'll draw a point. Here's its r hat vector. And here is its phi hat vector. Recall that these are both going to lie in the xy plane. They span the xy plane. And they are orthogonal to each other. Now, by the right-hand rule, I have r going in this direction and phi going this way. So z is going to be coming out of the light board. Okay, so I'm going to have, or my resultant vector is going to be in the z hat direction coming out of the light board is what I should have said. Okay, so now I have r times another copy of r squared phi dot z hat is L. Good. Now the important thing is that z hat is a constant vector. It doesn't change if I take a derivative. So I can actually go ahead, let me squeeze it in down here, and take a derivative of L with respect to time. What I'll get is, from the first term, 2r dot, and then times phi dot z hat, plus, now if I take a derivative with respect to phi, r squared phi double dot z hat. Okay, great. Now, it doesn't really seem like I've done anything particularly useful. I haven't gotten any closer to being able to use Newton's second law for rotation to determine the trajectory of an object. However, often we find ourselves even in a more special case than the case of planar motion, namely the case where the motion is constrained to lie on a circle. So if I have motion constrained to a circle, and let me say it's a circle of radius r, I'll use capital R here, then L dot will be equal to, well, the r dot term will vanish. So I'll just get little r squared, but that's equal to capital R squared on this circle, times phi double dot z. I've already said that tau is only going to have an effect if it points in the z direction. So this would be tau times z hat. And now I can use these two to form a differential equation that I could actually solve. I would have r squared phi double dot is equal to tau. And then I can solve this if I know tau. So this gives some sense that actually in certain cases, I have something like the same situation that I have for linear motion, wherein the laws allow me to calculate trajectories of objects. Now, the next thing I want to get to is an even more surprising consequence of the conservation of angular momentum for certain kinds of systems. It's a really cool example, and I'll join you back at the computer to go over it. All right, the example that I'd like to give for angular momentum for a single object is going to take us a little bit into vector calculus, which is a topic that some students may be not that comfortable with yet, but it's so good that I feel like we just have to do it anyway. And it concerns Kepler's second law, which says the following. So Kepler, let's see if I can get it to snap to something. There we go. Kepler figured out eventually that planets orbit stars in ellipses, and he realized the following. If I look at two regions bounded by the orbit of a planet, so here's the star at one of the foci of the ellipse. If I look at two areas, swept out by equal times of the planet's trajectory, then these two areas are equal. Now, curiously enough, Kepler did all of the derivation incorrectly. Kepler published his work in 1609, about, 80 years before Newton's Principia, and had all kinds of ideas that would become outdated before the end of the 17th century. For instance, he thought that the force was proportional to the velocity, or I should say not proportional to the velocity, but the magnitude of the force was proportional to the speed of an object. And he also thought that planets obeyed an inverse law rather than an inverse squared law due to the gravitational attraction of their stars. But nevertheless, he managed to come up with the result, which Newton later showed was correct. It turns out that this result is intimately related to the conservation of angular momentum. And to do it, we're going to need to think about how surface integrals work. So let's suppose that I want to take a surface integral of some surface that lies in the 2D plane. Okay, so here's my surface, and suppose I actually only want to take the integral of this part. So this is a sort of more general case than what I talked about above. All right, so I want to take the integral of this area, let me call it U. Now there's a way to do this using the surface integral of a particular vector field. Okay, so I am going to say that this is in the xy plane, and so the z hat vector points out of the screen. All right, so the area of U turns out to be equal to the surface integral, I'll use a double integral symbol here, over U of z hat dot the dA vector. Recall that dA vector is the vector normal to the surface with magnitude dA scalar. And dA scalar is a thing such that when you integrate it over a region, you get back the area of the region. So all that this says is that because this surface lies in the plane, its normal vector points in the z hat direction. So if I dot its normal vector, its area normal vector with the z hat vector, I just get back the integral dA of u, which by definition is the area of u. So nothing crazy has happened yet. But I do get something crazy happening once I start actually working with this thing. So let's do it. How do we compute something like this? Well, the answer is that we need a formula that you would get in a vector calc class. If it's a 2-semester vector calc, then this would be in the second part, the integral part. Okay, so what it turns out that we need is a parameterization. Okay. Now in this case, this curve that I'm showing on the outside is supposed to be the trajectory of a particle. And I'm going to call that trajectory r of t. Again, it's in the plane. I'm doing everything for an example where I have everything in the plane. So I have a trajectory that I can use right off the bat. I'm going to say that a point u in the plane is parameterized by s and t. And my parameterization is as follows. It's going to be s times r of t with t between, well, we need some values. So let's say that this is the point where the particle, the point in time t1 where the particle enters the region u, and this is the point t2. Okay, so I'm going to have t between t1 and t2, nothing surprising there, and s between 0 and 1. So that way I know that I get everything in the middle because I never leave, I never go past this boundary where the particle actually travels. All right. So now how do I actually get this? For that, I'm going to need a formula, which I'm just going to pull from Wikipedia really quickly. Okay, and we're back with that formula now on the page. So for us, V is z hat. Maybe do this in another color. V is z hat. ds is what I'm calling dA vector. And r vector is what I'm calling u vector. So pay attention to the differences here. Okay, the t is the region being integrated. So that's this region here. For us, it's a rectangle in the s and t space. So here's t, here's s. So s again goes from 0 to 1. T, maybe it's a rectangle that doesn't go through the origin, goes from t1 to t2. So we're going to integrate over that rectangle. But what are we going to integrate? Well, it turns out we're going to look at this last line here. We're going to integrate the following. So again, I'm trying to calculate the area of capital U. And this is equal to, so I'm going to call this region S goes from 0 to 1, T goes from T1 to T2, and my V now is this vector field evaluated at that point. But this vector field, for us, is just a constant vector field. So nothing is going on there. This is just the z hat vector field. Then we need to take a dot product. And we take a dot product with u with its partial taken with respect to s. Okay, so let's do that up here. The partial of the u vector field with respect to s, well, look, s appears as a linear factor, so that's just r of t. Okay, so r of t appears where Wikipedia's formula had dr ds. Now dr dt. So up here, all I need to do is take a t derivative of this. But look, that's going to give me back the velocity times s r dot of t. Okay, so I'm going to have r of t cross s r dot of t ds dt. Great. All right. So what do I need to do now? Well, I can pull this s out here. Meanwhile, what I have in the middle is sort of miraculous. I have an r times r dot. But that, if I multiply by the mass, is exactly equal to the angular momentum at time t. So I'm going to get these two integrals, nothing changed there, t1 to t2 of s z hat dot L of t ds dt. Okay, now we're doing something. We're cooking with gas. So it turns out that this s only appears here. So this is just the integral of s from 0 to 1. Okay, so the s integral I can carry out really easily. The integral from s equals 0 to 1 of s ds is equal to 1/2 s squared evaluated from 0 to 1, which is just 1/2. Okay, so I get 1/2. Oh, and I forgot it's not L, but rather L over M. Got to make sure my dimensions are right. Okay, so anyway, I have 1/2 times the integral from t, going from t1 to t2 of z. And actually, why don't I just pull out my m? So I'll have 1 over 2m z dot L of t dt. Okay. Now, there's one more thing that I can do here. It's not the most important, but I might as well do it, which is that I have planar motion. Anytime I have planar motion, I know that L lies in the z direction. And that's because, again, if R lies in the xy plane and P also lies in the xy plane, then, so if this is R and this is P, then their cross product lies in the direction that is perpendicular to both of them. Since they're both in the xy plane, L must come out of the plane. So this is actually equal to 1 over 2m times the integral from t1 to t2 of just the magnitude of L dt. Good. Okay, so now I have something here, but how does this give me that these two areas are going to be the same? Well, if I have angular momentum conserved, if I'm working with a system for which angular momentum is conserved, then L is a constant. So that would imply that the area of U is equal to 1 over 2m times the integral from t1 to t2 of just a constant L dt. But now I'm just taking the integral of a constant. So this is just going to give me L over 2m times let me say T2 minus T1. In other words, if two regions are swept out in the same amount of time, T2 minus T1, then they will have the same area. So this proves Kepler's second law, sorry. But actually, it proves something even bigger. It proves that anytime you have a system for which angular momentum is conserved, you always have an analog to Kepler's second law, that the area swept out by the trajectory, if that trajectory forms a closed curve, the area swept out in a given amount of time is simply proportional to the amount of time. All right, there is one more thing, right, which I've argued elsewhere in the video, but I want to make sure that I state clearly really here, which is that we do need to show that angular momentum is conserved. In this case, angular momentum is conserved because there are no torques. In the situation that we're looking at, this star, the planet, sorry, so let's say this is the planet, is being pulled on by the star, which lies at the focus. But we're looking at the region swept out by the line between the planet and the star. And we know that the star is pulling the planet toward itself. Therefore, there isn't any torque in this case. And that's just because, again, if we take the star to be at the origin, the force vector points from the planet to the origin. In other words, it's collinear with r. So no torques implies angular momentum is conserved. All right, let's hop into, let's hop back to the light board, and we can keep talking about angular momentum as it applies to systems of more than one particle. Now, we haven't yet discussed Newton's third law for rotation. Let's kind of think about what we would want for Newton's third law, or maybe what we would expect for Newton's third law. We would expect something like, if an object A exerts a torque on B, then B exerts an equal and opposite torque on A. So let's see if that happens by drawing a little diagram. Okay, so we'll let these be the x and y directions, and here will be our first object, A, and here will be our second object, B. Okay, now I'll say that they exert forces on each other. So in particular, let's draw in the vectors to each of these. And for no reason at all, let me imagine that B exerts a force on A, which points down A's vector, down A's position vector. So I'm going to say that's F A on B. That's the force of B on A. That means by Newton's ordinary third law, let me move my label here, that A exerts a force on B that's equal and opposite in direction. So this is FBA. So what's the point? The point is that FAB is collinear with RA. So B has now exerted zero torque on A. So tau AB is equal to 0. However, we can look and see that tau BA is not going to be equal to 0. So tau BA is equal to RB cross FBA, which is not equal to 0. So this cannot be correct. And in fact, there's no way that we can make it true unless we make a particular assumption. So here's what I'll say is Newton's third law for rotation. If objects A and B exert central forces on each other, then tau AB is equal to minus tau BA. Now, a central force we need to define. A central force of, let's say, B on A is a force parallel to the displacement between A and B. In other words, FAB is parallel to RB minus RA. Okay, let's get a marker and draw in what happens in this case. So let's imagine now that these two objects are pulling on each other. This one is dead. Not showing up super well. But anyway, if these point in the same, along the line between A and B, it turns out that those torques do cancel. And let's go ahead and prove it now. Okay, so using the original we want to be able to prove the new. We don't expect to be able to prove the converse direction. This law is not as general as Newton's third law is, the original Newton's third law. But let's go ahead and prove it. So tau AB, let's say, is equal to RA cross FAB. Okay. Tau BA is equal to RB cross FBA. Now let's just subtract these two from each other. So we get tau AB minus tau BA is equal to, well, we're going to get RA minus RB. Oops. Sorry about that. We're actually going to get RA cross FAB minus RB cross FBA. Now we'll use Newton's third law, which says that FBA is equal to minus FAB. Good. And I'm making a mistake here. I shouldn't subtract these two equations. I should add them. So everything I wrote is true, but it's going to be much more useful if we do this. Now we'll pick up a minus sign here. But notice we can pull out an FAB from both terms at this point. So we'll now get RA minus RB cross FAB. Okay, good. But if FAB is parallel to this difference, this displacement, then this is equal to 0. So this is now equal to 0. So tau AB is equal to minus tau BA, just as we wanted. All right, so now we have an analog of Newton's third law for torques. This kind of completes a project of figuring out how to analogize Newton's laws for angular momentum. But what we still have to do is figure out if we have that kind of way of aggregating a whole collection of objects and treating it as a single object living at a given point. So I'm going to erase the board and we'll get right to that. The last item on our agenda for this lecture is to consider collections of particles and their angular momenta. Okay, so before we had collections of particles and their momenta, and we defined the following objects. We defined M to be the total mass. We defined R to be the center of mass. We defined P to be the total momentum. And we came up with a really useful relation. mr dot is equal to P, which we argued means that we can treat the whole system, if we don't care about its internal dynamics, kind of like a single object that's living at the position r. That effective object has the same momentum as the total momentum of all of the objects in the collection. We would love if something similar were true for angular momentum. So let's kind of check and see if that's true. So what if we define effective angular momentum of the center of mass? And we kind of see how we should do it, right? If we treat r like it's the position, capital R like it's the position of an object, and capital M like it's the moment or the mass of an object, then we could say that L, our effective thing, Cm, should be equal to, well, R cross capital M R dot. Okay, let's see if that gives us the same thing as the total. So compare with L total, which would just be L1 plus dot 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 plus Ln if we have n objects in our collection. Okay, so let's expand this first thing. LCM is equal to, so for the first one, we need to take a sum. I goes from 1 to n, or maybe actually it's just easier to write this all out. So we'll have m1 r1 plus dot 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 plus mn rn over m cross m times r dot. Now this m is actually going to just cancel out the m that's in the denominator of r dot, and so we'll just get m1 r1 dot plus dot 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 plus mn rn dot. Okay, now let's look. We'll find something interesting. So notice if I cross this term and this term, that is almost going to give me the angular momentum of the first object. It's going to give it to me except weighted by m1 over m. If I do it for the second term in the sum, which would be m2 r2, and cross it with the second term in this sum, I'm almost going to get L2. So it looks, but also weighted by m2 over m. So it looks like what I get is the following. I get m1 over capital M, L1, plus dot 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 plus mn over capital M, Ln. But then I also get tons of other terms. So like I, for instance, get m1 r1 cross m2 r2 dot. So I'm just going to say plus cross terms. And we can check, even for two masses, these two are definitely not equal. So we cannot, in principle, even sort of in theory, treat the whole collection of objects like a mass living at the center of mass for the purposes of rotational motion. It just doesn't work. However, we can go a little bit further with this. However, we can push our analogy a little bit further if we remember that we can use the center of mass frame. So what I'm going to do is assume that we're working in a frame B when computing the total angular momentum. And I'm going to say that frame A is a center of mass frame. Furthermore, I'm going to assume that there's no rotation between the two. It just makes the calculation a lot messier. It's not that it wouldn't work. Okay, so that means that RB is equal to RA plus capital R. In other words, to get to the position at B from a center of mass frame where R is at the origin, we just need to add whatever the position was in frame A to the center of mass. All right, good. Maybe a little diagram is in order. So if this is frame B and this is frame A, here's B, here's A. Then this is the position of the center of mass in B. And suppose that we have a particle or an object that's right here. So its B vector is this RB. And to get there, we just add R and its A vector, RA. Okay. Good. All right, now we have this, so let's take its derivative, assuming that we're talking about the trajectory of an object. RB dot is equal to RA dot plus capital R dot. Nothing particularly interesting there. Okay, now the next thing that we need to do is express the total angular momentum in B as a sum. So I'll go I goes from 1 to n of L, B, I. All right. And then I'll write this out in terms of these objects. Okay, so I'll get this sum from 1 to n of R, B, I cross M, I, R, B, I dot. Good. Now I'm going to re-express each of these in terms of A. I goes from 1 to n of R, A, I plus capital R. Now note that this doesn't depend on which mass we're talking about. Cross Mi times R, A, I dot plus capital R dot. Okay, good. Okay, so now there are certain terms that I can start working with. The first one will be if I take this and cross it with this. Those two terms, when crossed together, that just gives me RAI cross MI RAI dot. That is precisely the angular momentum of I in A. But I'm going to add those all together. So my first set of terms is actually going to give me L total A. Good. The next thing to do will be to cross this with our capital R dot. So let's do that. So we get plus the sum over I. Actually, all the rest of the terms will depend on that sum, so let's keep the sum in here. So we're going to get RAI. I'm actually going to move the MI over here and then cross R dot. Okay, the next thing that we're going to do, I'll use wavy lines, I guess, for this, is cross this with this plus R cross MI RAI dot. Okay, and then lastly, we get this term. So we're going to cross R with R dot. The only thing that depends on the sum here is MI, but actually, this can just be summed over to give us capital M. So then, plus R cross M R dot. Great. Now, I want to take a look at this last term, because this is exactly that object that we were hoping would be useful. This one here, LCM, the effective angular momentum of the center of mass. Let's come up to the top of the board and keep working this out. Okay, so we have L total B is equal to L total A plus these two terms plus this last term. But let's think about these two terms here for a second. R dot doesn't depend on this sum at all. So really this just becomes a sum over MI RAI by itself. But this is proportional to the position of the center of mass in frame A. And the proportional of this, the position of the center of mass in frame A is exactly 0. So this term is 0 because it's a center of mass frame. But check it out. This term is now just the derivative of this one. Or I should say this factor is the derivative of this one, but that one was 0, so this one is also 0. So in the end, we just have LA total plus LCM. Fantastic. So what was the point here? Well, we can't treat this collection as if it's a single object that lives at position capital R, and then simply calculate the trajectory of capital R to figure out the angular momentum of this effective single object. Instead, there's something a little bit more subtle going on. It turns out that the angular momentum in B is the angular momentum of that effective object. So let me write that in. This is the angular momentum of the effective object of mass m, capital M, and trajectory capital R. But then the collection has to be treated as if it has some implicit, so internal angular momentum, some extra angular momentum, and that is encoded here. So this is the sort of intrinsic angular momentum of the collection. Great. And this is the angular momentum that we calculate going to the center of mass frame. So wonderful. That's all we needed to do. So this concludes our lecture on angular momentum. Obviously, this lecture has been quite conceptual and we've gone through a lot of material. So I urge you to find a textbook and try doing some problems with angular momentum to get more familiar. We're going to move on in the next lecture to talking about energy. Thank you so much for watching, and I'll see you then.